Good morning, everyone. My name is Brett Carpenter from the University of Oklahoma. I was co-chair with Elizabeth Catherine of the Fault Mechanics and Earthquakes Working Group. It was a really interesting group. We had folks from seismology, structural geology, rock mechanics, myself, and even some dynamic fault modelers that had joined the group. So kind of really think about breadth and the types of data that we need. I'll say as well, for Matt, I am also the only one of my working group here. So please give me all the credit, blame all them for the But you'll see my talk is a little bit short, so you'll get to hear me riff a little bit. I get mixed reviews from my students on that, but we'll see where this goes. All right, so our working group, we had a series of meetings as mostly, and really trying to talk about the current status of what we know about fault mechanics and earthquakes from previous scientific drilling and what we could look for in the future. This is a kind of a quick aside, which you'll get more of. I led the 2018 Earthquake Synthesis Workshop looking back at SAFE. It's basically compiling the history of the SAFE project and documenting the challenges, let's call them, and successes from that project. And so that kind of led us to discussions on that project, DFDP, the Alpine Fault Drilling Project, and others. But we started off from kind of fundamental understanding that we still really don't have a great idea about what happens on or near faults in fact. We can go and look at exposures of the outcrops and things such as that, and run our experiments in our labs, but actually understanding the conditions, the changes in conditions, the state of stress at that, something we still just fundamentally don't have a good handle. And this becomes an issue, let's say, in the sense that if we're running experiments or doing modeling runs, we're not running with the most relevant input data, either data from the right type of altered samples or the right temperature ratios. I'll note kind of in the sides for some of my work. I worked on deforming Oklahoma basement rocks that we had collected from cores around the state. Highly altered. Actually worked with OGS, and that data was input into the Oklahoma Corporation Commission mitigation models for seismicity, updating the previous literature from Brandon. And so there were direct applications for that fundamental research, and it was from borehole core samples and realistic experience. And also with Matt, we're a big proponent of long-term monitoring in the subsurface. If you're monitoring seismicity in the subsurface, it's a lot quieter than surface stations, so you can see a lot more when you monitor in the subsurface. And what things that we can get out of this in terms of the big picture, better constraints on earthquake size and perhaps earthquake forecasting. With better inputs and more models, we can better understand the earthquake process from a fundamental side, so fundamental earthquake physics. And then, as I mentioned, that data goes into important mitigation and forecasting issues, whether it's mitigating CO2 sequestration, wastewater disposal, or looking, let's say, at earthquake early warnings and understanding some of those concepts. So our first scientific question. So we have kind of an applied question and a fundamental question. So the first is how do earthquakes start propagating stuff? Kind of put it simply. I grabbed this little image here from Brendan last week of Cornell from his 2-meter fault. Only as kind of a motivation that in that lab experiment, we have great data on kind of how some of the earthquakes propagating along that meter fault. And the idea is that with additional kind of borehole data and characterization along faults, we can get a better understanding of the complexities in the earth, understanding how those happen. During earthquakes, there's this amazing interplay between aseismic slip, stress transfer, earthquake nucleation. That's almost impossible to tease out inside the ground. We just don't have the resolution to really be able to pull out those complex interplays. So kind of looking at how those alter and change at depth or evolve at depth will give us a great idea. in terms of fundamental physics. What triggers the initial slope? Most of us are familiar with, the more cool and failure plot where, all reaches a critical stress state that starts sliding. Not always the case, but also doesn't predict the type of sliding that will happen. So to really kind of fundamentally understand that. And then this final one, which is something I've been involved in both in the lab and in field measurements. Are there any precursor signals before an earthquake? Those could be seismic signals, those could be strain transients. Is there something that exists that is measurable in the field? The answer is yes in the lab. And there are theoretical determinations that support that as well. But if we instrumented, let's say, near a known earthquake patch, could we watch the earthquake nucleate in real time? And so that's a fundamental question that our group was interested in answering. The second question, as I kind of mentioned, faults are at depth greater than 3 kilometers. Spreadsville faults in Oklahoma. What are the rocks? What are the rocks? How do they evolve with time? It's not a static system. Stresses change, fluids change, rocks become altered. So what really are these basic fundamental properties? I showed this picture from the SafeLab project, one because I had easy access to it. But what I'll note from the SafeLab drawing, if you look at the outcrop of the SafeLab near Parkville in Central California, it doesn't look like that. So the outcrop sampling of that fault from the surface, gave us basically the wrong story for what to expect with that. Not that it was incomplete, so we had access to, but it wasn't giving us what was happening with that. We didn't understand that we were going to encounter a gouge-wide drainage zone. We didn't understand the importance really of fluid chemistry and altering the rock over time. So there were a lot of things that we couldn't understand from looking at the surface outcrop of the same fault. And so this is where sampling that becomes really critical in terms of our basic understanding. There's a lot of different fluid transport regimes. Faults are great at moving fluid along them, but very, very good at preventing fluids from moving across them. So thinking about that and those different chemistries over time, in terms of thinking about the temperatures, when I was in New Zealand, we were basically looking at 100 degrees Celsius per kilometer in the hanging wall of the Alpine Fault, where it was being got pretty toasted. There was a little mishap. We had some hydrothermal fluid flow from the well at one point. Whoops. But it showed you that, in this case, that would bring the seismogenic zone, so the earthquake nucleation zone, up toward the surface. And that was a pretty new result, only gathered through scientific drilling in that case. And so knowing these things leads us to a lot of areas where we can think about applying either geothermal or critical minerals. I've had the fortune of looking at a bunch of cores from northeast Oklahoma, which is the tri-state mining district, and actually looking at the critical mineral cores and such in the rock. So really thinking about how fault mechanics and earthquakes apply to these fields. So we spent quite a bit of time thinking about what would a potential project look like. And this is perhaps what generated the most, let's say, heated discussion in my working group, was trying to kind of identify the outlines of a future project. And one was there needs to be faults, either, or there needs to be a good expectation of fault slip in the time of the drilling project. So kind of 2 ways to approach that: go to an area that's actively slipping, either naturally or genetically, or run an in-situ experiment where you make them. So that kind of led to those two possible projects. We've come to really understand that we actually need to know much more what the volume of the rock is doing around the fault in terms of its elastic properties and stiffnesses. So while it's great to know what actually is on the fault, we now know that between the damage and stuff, we see these changes in stiffness and other properties approaching. So, we really need to have a good 3D characterization around the fault. The area needs to be logistically accessible. we put that in there. It's just prior to some of the working group meetings. I've been talking with Steve Hickman about the renegotiation of the lease on the Kester property for the Save by Borehole. So, long-term access and easy access is important. And then also a well-defined target. And then, as I said, finally, if we can leverage other activities that are happening. So ongoing anthropogenic seismicity, other data sets, that would be a strong plus. And so some of the recent areas that are recent ideas in these Lake Visible research endeavor with John Farmer. I'm looking at the fault loading and stress state at depth. Well, I held a workshop in Oklahoma in 2018 meant to really look at what was going on in the shallow Oklahoma basement in the sense of we're dumping wastewater into the formation above the basement and triggering magnitude 5+ earthquakes in the basement. Why? There was a group looking at inducing faults, looking at the seismic project. That's that kind of middle figure, where the idea really was to find a location, really in the near field and at high rates, instrument the fault and cause an earthquake, right? To actually be able to recreate what we can do in the lab, and then see what would happen and basically kind of extend some of the previous projects that were done in other regulatory environments, let's say earlier, looking at various seismic and using experience. There's been discussion over the years about returning to SAFOG and using the existing facility that's there, which is a borehole at 3 kilometers depth, maybe 500 meters away from repeating rivers. So going back and reusing that facility either to, let's say, drill straight through the earthquake patch, sample it, and instrument it, or drill parallel to the earthquakes and the fault and watch the transient strain deformation that happens during earthquakes. So there's been some proposals to go back and to do that. And I'll say, the bottom 4 are basically in the discussion workshop phase at best. The Libre project is kind of working and moving forward, and Jonathan gave a nice presentation at GSA recently on that. So, kind of necessary resources, things that we think we identify as needs going through it. Really kind of guidance and assistance in really combining different funding streams into a workable project. That was something that we talked about. PIF, that's planning and management resources. There's a lot of people that have worked on projects now. It's a long-term commitment and it takes quite a bit of effort. But then also specifically, we've seen with great success some of these rapid response drilling projects get out to be able to instrument and sample faults and capture the transients and permeability, transients and stress. So the flexibility to have some of these very quick response projects. In terms of data, we all need site characterization, data repositories. And then a lot of the things that are available up at the facility in Minnesota in terms of core handling and sampling. And in terms of technology, since SAFOG wrapped up in 2007 or phase 3 wrapped up, the leaps and bounds in terms of borehole instrumentation, and whether it's fiber optics, in terms of just a long fiber optic strain meters, hardened tools that can survive elevated temperatures. So those continuing trends gives us a lot better chance for kind of long-term monitoring in the subsurface. And that last point there, our industry friends have also gotten a lot better at horizontal and deviated drilling and targeted drilling. And so utilizing that fact that we can very kind of precisely now aim where we want that drill bit to be in the subsurface. Areas of overlap. My co-chair and I, Elizabeth, kind of went through all the 2 pagers. To try to identify some areas of overlap with different groups. And as Matt said, with the energy transition, we certainly feel we have strong overlap with them in terms of geothermal and CO2 sequestration. On the hazard side, the fluid flow side along faults. So you need a lot of the same data, a lot of overlap in those groups. With geomicrobiology, thinking about how the microbes alter rocks at depth or have altered at depth, thinking about kind perhaps the biosphere, hydrology and critical zone. In one part, thinking about what happens when all surface rupture faults come up to the surface through soil. So thinking on that aspect of the critical zone. But also connecting really, shallow critical zone or shallow biosphere with deep biosphere. And then the folks in magnetic systems, let's say technology that can survive high temperatures, right? So how do we get at seismogenic depths? And for the end of the work, we try to identify kind of our vision and ideas for the future. And so first setting up these kind of large moonshot type drilling projects for human here. So the scale of SAFOD, or perhaps the scale of the size I'm suggesting, that's real hard for a single PI to carry that through, if not impossible from beginning to end. And there are other, there are, let's say, job factors that also get in the way of that. And so really trying to think of these large long-term projects, making them cross-discipline, so really distributing the work among multiple PIs, like equal PIs in the group, and these larger PI teams. And I think this third kind of bullet point really is a place where kind of some of the funding agencies and CSD can work with universities on, or at least giving, if someone's going to partake in one of these projects, considerations in terms of publishing, promotion, tenure, because I can tell you from the SAFOD timeline, where all the publications were in the SAFOD timeline. I mean, they're still occurring, but they were in the last 10 years of a 30-year project, right? So it was a slow burn, then all of a sudden, right? So kind of this consideration that doesn't work real well with 5-year time periods in academia. So some type of understanding or memorandums of understanding for a PI if they're going to take on a project like this. And then presenter's choice, because I'm here and they're not. And thinking about identifying a project or maybe projects where the fault mechanics and earthquakes community can kind of join up and pull together. So kind of a community type project, which is a little different model than this kind of separate PI proposal project. And that's all I have. So thank you.